Well, we finally made it to gas laws. Gas laws are fun. There are a lot of math, which is relatively simple, so most of you are going to probably like this chapter. Also, it's a lot of stuff that you already know, which is great. You may not know that you know it, but you do. And so that tends to be a lot of fun because we get to really just work with things that aren't too difficult. And again, gases are a lot of fun. So we're going to talk about properties of gases, different gas laws, the ideal gas equation, different reactants, and when items will actually deviate from what we call ideal behavior, as well as the kinetic molecular theory. These are your suggested chapter problems for chapter 9, and here we go. So, properties of gases. Gases have mass. So if I were to fill up a balloon with air, it's going to sink because the density is going to be higher than what we would think if we filled up a helium balloon, right? So helium has a lower density, it's going to float. But if I blow up a balloon with air, since it has the same density of the air around it, and then the material from the balloon, it's actually going to sink. It's not going to float. So gases do have mass, and that mass, remember, density is equal to mass divided by volume. We can also relate that to the density of a gas. Gases expand to completely fill their container, which is great because if we're all together and gases did not expand to fill their container, then we would all be huddled in the corner trying to breathe air, and we wouldn't have air everywhere we go. So it's really great that they do that. If we were in the classroom and I were to open up a bottle of perfume, then we would be able to smell it in the back within no time at all because that's called diffusion. Gases move through each other easily. Gases can be compressed. Many of our homes use this when we use propane or something like that. Compressed gases are used in almost every type of work environment. So I used to work for Airgas, and when I did, we delivered to every single type of industry that you can imagine. Different gases can move easily through each other. This is diffusion. Gases exert pressure. The gas particles hit the walls of the container, and pressure is force over area. So force over area is equal to pressure. So this is where we have pounds per square inch, or PSI. So pounds is the force, and then over the area of square inches is PSI. That's what we're used to in America. We're going to learn some other units that we use in science. Gas pressure is also a function of temperature. You know this. You take a balloon and it's all filled up and you walk outside and it's cold out. What happens to the balloon? I hope you all said it shrinks, right? So it shrinks down, shrivels up, but then when you bring it back into a warm environment, it tends to reinflate. Because the temperature goes down, the pressure goes down. Gas properties are almost independent of their identity. Because gas particles are so small and the area between them is so large, they actually doesn't really matter what the gas is. They're still going to behave the same. They're going to have the same properties. Now, reactivity, chemical properties will be different. Properties in how they behave. Their behavior is going to be independent of their identity. So I just want to know, would you lie on a board with one nail in it? I wouldn't. I couldn't even find a picture of that on the internet. That's how hard it was. So why would you not lay on a board with one nail in it, or even step on this nail that has two nails? Hopefully, it probably made you cringe, right? Because the pressure is so great. So this would have great or very high pressure because the force would be great over a small area. So would you lie on a board with 20 nails in it? I wouldn't. But this guy laid on one with like 12, but I'm not sure how he got up and down, and he also looks maybe like a circus performer. So even though the pressure is less, than the last picture, it's still too high for me. I wouldn't want to lay on that. So we have a greater area, so we still have force over a greater area, but it's still not spread out enough for me to want to lay on it. So how about 420 nails? And most of you might have said yes, and you can actually do this at a lot of different places, maybe a conference or something like that, where you can lay on a board with 400, all these nails in it. But the reason why this one isn't so bad is because even though the amount of force remains the same that your body is pushing down, the area is greater. So that means that the pressure is lower. So we won't feel that pain in one area. It's got to make sure that all the nails are the same height and that you get on and off very carefully. So pressure is force over unit area. We are used to PSI, or pounds per square inch. So this would be the pounds and this would be the square inches, because area units are always squared. Now we're not going to use that very often. In science, we use some different units, and these are some of the units that we use. So 1 atmosphere is the pressure that is basically what we're at around our environment. We're used to about 1 atmosphere. 1 atmosphere is equal to 700 millimeters of mercury. This is also equal to 1 torr. So 1 torr is equal to 1 millimeter of mercury. This is for Torricelli, who is credited with inventing the barometer. They've named a unit after him to try to give him some credit, and it didn't really pick up and remove the other unit. So now we just have an extra unit. 1 bar is equal to 1 times 10 to the 5th pascals, and 1 atmosphere is equal to 101,325 pascals, or 101.325 kilopascals. So that's just a unit conversion to kilo. Now, this is our SI unit, but this one is actually more common because this is such a large number for what we're at 1 atmosphere. Now, there's only a couple that you're going to need to know. You need to know 1 atmosphere is equal to 760 millimeters of mercury, which is equal to 101,325 pascals. So those are the ones you do need to know. So in this chapter, we're going to relate a lot of things to particle motion. So I'm going to erase the ink. So one thing that we can look at here is the kinetic energy equation. The particles are constantly moving. So when they're constantly moving, they're hitting the walls of their container. And when they hit the walls of their container, they are exerting force on the walls of the container. That force divided by the area is where we get pressure for these particles. So what happens if we increase the energy? Well, how can we increase the energy? Kinetic energy, well, we could increase the temperature. Temperature could go up. If temperature goes up, the particles have more energy. If the particles have more energy, the mass is not going to change. So what can change to make this remain equal is the velocity, so the speed of the particles. So if the speed of the particles changes, they're going to hit the walls more frequently. So if temperature goes up, pressure will go up. So we're going to be able to relate a lot of our temperature, pressure, volume correlations to this kinetic energy equation. So you might want to know that just so you can relate things in your head. We probably won't be calculating anything with that as far as what is the velocity of the particles or anything like that, but it is a good way to look at how they are related. So liquid water versus gaseous water. So we look at water a lot. We use water. 1 mole of water is approximately 18 grams. So if we're to look at what amount of volume that is, so if we look at 1 mole of liquid water, it actually takes up less than half of a golf ball. So half of a golf ball. That's not a lot of space. But 1 mole of water vapor, so gaseous water, takes up more than 3 volumes of 3 basketballs. So the same amount of water, this is the liquid form, that takes up just half a golf ball. If we were to vaporize it, takes up more space than is in 3 basketballs. So the particles are so far apart in a gas that they actually feel like they have no neighbors. They are very far apart. Standard temperature and pressure is something that you are going to have to know what it means for gases. So STP for gases is 0 degrees Celsius or 273 Kelvin. So I usually remember 273 Kelvin because after that I can convert to anything. And 1 atmosphere. So I remember it as those, and I can convert to any of the other units if I need it. But these are all the pressure units. And these are the temperature units. Now, notice I don't have Fahrenheit in there because we don't use Fahrenheit in science. The ones with the asterisks are exact numbers. So you'll notice the ones that are not exact numbers have 6 significant figures, so they're really not going to limit your significant figures. And again, we don't use PSI that much. So if the pressure is 0.920 atmospheres, what is this in millimeters of mercury? So we're going to do a unit conversion just like we've been doing, 0.920 atmospheres. Our unit conversion is going to be what we had on the previous slide. 1 atmosphere is equal to 760 millimeters of mercury. So 1 atmosphere is 760 millimeters of mercury. And so if we take 0.920 times 760, we get 699.2 millimeters of mercury. Sig figs, we can only have 3 because this has 3, so this would be 699 millimeters of mercury. So what is that answer in torr? Well, 699 millimeters of mercury. For every 1 millimeter of mercury, we have 1 torr. So it would be 699 torr. Because remember, torr and millimeters of mercury are equivalent. Good, so simple unit conversions, you just have to know those 3 that I mentioned. And we'll keep going. So given 465 millimeters of mercury, convert to torr and atmospheres. So pause it and try it. Starting with 465 millimeters of mercury, there are 760 millimeters of mercury in 1 atmosphere. So 465 divided by 760 should be 0.61184211053, or 0.612 atmospheres. And torr is going to be 465 torr. They're the same. And here it is written out in the PowerPoint for you. Good. Hope that went well. You can practice some of those if you need to, but they're just unit conversions where we have those. 1 atmosphere is equal to 760 millimeters of mercury. 1 millimeter of mercury is equal to 1 torr. And 1 atmosphere is also equal to 101,325 pascals. So those are the conversions you need to know. So the air around us is constantly exerting pressure. How do we measure it? A barometer is how we measure external and atmospheric pressure. A manometer is how we measure the sample of an enclosed gas. So this would be in a reaction vessel. And this is just our everyday surrounding pressure. So this is a barometer. A barometer is a glass tube. So the glass tube is filled with mercury and it's inverted into a pool of mercury. So when this comes down, this is actually a vacuum at the top. So that anytime that the pressure of the atmosphere pushes down on the pool of mercury, it forces the mercury in the tube to rise. At 1 atmosphere, the height of the mercury is 760 millimeters. That's where 760 millimeters of mercury comes from. So if it goes down, so if the pressure were to be lessened, so if this were to actually not push as hard, the mercury in the tube would go down and it would be less than 760. So that's how a barometer works. And that's where the 760 comes from. This is a manometer. This is an open manometer because it's open to atmosphere. There's no vacuum here. It's not sealed. So the pressure of the atmosphere is pushing down here. So atmospheric pressure pushes down. And if this is open like it is, the gas sample pressure is pushing down. I can look at this and say, well, the pressure of the gas must be less than atmospheric pressure of 1 atmosphere because this is being pushed down further. So it's kind of like a teeter-totter. If this one is pushing harder, then it would be here and this one would be up. So it would look different. But since the atmospheric pressure is pushing the mercury down further than the gas in our sample, we know that this has to be less than atmospheric pressure. So we know that much. So it's an open and a closed. If it were closed, this would be sealed and it would be a vacuum. And I have a picture of that on the next slide. So this is a closed manometer and this is an open manometer. So we compare this one to atmospheric pressure. This one, we're going to take the height difference, and the height difference would be equal to the pressure of the gas. So this is where we see this come in. And this here, the pressure of the gas is equal to pH plus the atmospheric pressure. So pH could be negative. So here, the gas pressure is actually greater than atmospheric pressure because it's pushing down further than the atmospheric pressure. So Boyle's law is our first law we're going to talk about. And Robert Boyle studied the relationship between pressure and volume. So what he did was he measured the volume of air at different pressures using a J-shaped tube that had trapped mercury in it. So this is what he did. And he discovered a relationship between pressure and volume when the gas was confined, and the number of moles and the temperature were kept constant. So the only variable we have here are pressure and volume. So we were changing one of those and looking at the reaction of the other. So moles and temperature were constant. And that's important. So we have to make sure those are kept constant in order to talk about pressure and volume. Otherwise, it'll be a different relationship. So what Boyle saw was that as volume increased, pressure decreased. Now that makes sense. If we have a room about this size, and I asked you guys to get up and start running across the room and hitting the walls, okay? But then I doubled the size of the room. Would you be able to hit the walls as fast, or would it take you longer? So if I double the size of the room, it's going to take you twice as long to run back and forth and hit the walls. So the pressure will decrease. So this is known as an inverse proportion. As one goes up, the other one goes down. So we can say that pressure and volume, this is what a graph of an inverse relationship looks like. I'm going to say pressure times volume is equal to a constant. And we use K for constant because sometimes C is actually used as a variable. So pressure times volume is equal to a constant. As one goes up, the other one goes down, so this will remain constant. And that's what we have here. Volume is inversely proportional is what that means to pressure. So what we see here, this is P times V is equal to K, a constant. So this is actually showing you that pressure at 1 atmosphere has a volume of 1 liter, and pressure at 2 atmospheres, so double the pressure, has half the volume. So one thing to keep in mind that honestly, it's embarrassing how long it took me to realize this. When you know these relationships are equal to a constant or whatever, you can make up values and see what happens. So a lot of times, multiple choice questions or questions on standardized tests like to ask you, if I double the volume, what happens to the pressure? Just make up numbers and figure out what happens, and then you'll be able to figure it out mathematically. So if the pressure is doubled, if the volume is doubled, the pressure is going to be cut in half. So if we know the pressure and the volume under one set of conditions, you saw me write P1 V1 is equal to constant. And then if you looked on the slide that was from the book, it said PV is equal to constant. Well, I wrote P1 V1 because if I know the pressure and the volume under one set of conditions is equal to a constant, the volume and pressure under a second set of conditions must equal that same constant. So we can say, well, if I know under one set of conditions, I can figure out what one of the missing variables is under a second set of conditions. So P1 V1 is equal to P2 V2. That's Boyle's law. So let's try one. A sample of gas is enclosed in a container with a volume of 785 milliliters, a pressure of 0.867 atmospheres, If the volume is decreased to 565 milliliters, what is the new pressure of the gas? Now I'm telling you it's Boyle's law. So we know we need P1 V1 is equal to P2 V2. Now on the test, I'm not going to do that, right? So P1 V1 P2 V. I like to make a list because then I know exactly what I'm doing and I can just plug my numbers in and go. All right, so P1 is 0.867 atmospheres. V1 is 785 milliliters. The volume is decreased to 565 milliliters. What is the new pressure? So we're looking for P2. So we're going to divide both of these by V2 to get P2 by itself. So I have P1 V1 divided by V2 is equal to P2. And then I just plug my numbers in. First, I want to double check and make sure the units are going to cancel that are the same. So here I have P1, 0.867 atmospheres times 785 milliliters divided by 565 milliliters. So ask yourself what should happen. The volume went down. What should happen to the pressure? If volume is decreased, if we cut the room or make the room smaller, the pressure should go up, right? And if you look here, our answer is 1.20459292. So it did in fact increase. That's a good sign. And then we look for significant figures. I should have 1.20 atmospheres. And it just says of gas. So that's our answer. You try one. Oh, I can erase the ink. You can see it written in there if you really want to. A weather balloon contains 150 liters of gas and has a pressure of 1 atmosphere. At an altitude of 41 kilometers, that atmospheric pressure is only 0.4 atmospheres. At this new height, how large must the balloon be to support such a pressure? Please pause it and try it. Now we know it's P1 V1 is equal to P2 V2 because we're says the Boyle's law up here at the top. But how would we know that if it didn't? Okay, so it talks about a volume and a pressure, and it talks about another pressure and how large is a volume. So we're only talking about volume and pressure. So P1 is 1 atmosphere. The volume is 150 liters. P2 is 0.4 atmospheres. What is our new volume? So we're going to divide both sides by P2 to get V2 by itself. So P1 V1 divided by P2 is equal to V2. So I plug in my numbers. My units are going to cancel because they're the same. 1 atmosphere times 150 liters divided by 0.4 atmospheres. So the pressure went down. What must happen to the balloon if the pressure went down? That's what you should be asking yourself. 1 times 150 divided by 0.4. Yes, it should get larger. So 375 liters is going to be the size of the balloon. Let's look at sig figs. 3, so we have 4 here, 3 here, 3 here. So 3 in our answer, 375 liters. I didn't use the 41. That 41 is just there to tell you how high you are. So you're at an altitude of 41 kilometers, has nothing to do with the math of this problem. So next up is Charles' law. Charles was an avid hot air balloonist who studied the temperature and volume relationship of gases. So what he did was he actually used a gas sample that was trapped inside of a cylinder, and it had a moving piston. So something, like this with a piston coming out of it, and it had a gas sample trapped inside of here. And he would take this and he would put it in different temperature water baths and see what happened. Did the piston go up or did it go down? And what happened to that gas sample, the pressure of it when he varied the temperature? He actually got a lot more than he thought he would. So he actually found that the volume increased as temperature increased. But he also found the temperature scale, the absolute temperature scale. But let's take a look first at the graphical representation. So if volume goes up, temperature also goes up. What kind of relationship is that? So V1 over T1 is equal to a constant. All right, that is known as directly proportional. So as one goes up, the other one goes up. So actually, during his experiment, he was finding that for every 1 degree Celsius that the temperature changed, the volume changed by 1/273rd. Does that number of 273 look familiar to you? It should be, and remember this happened at constant pressure and the same number of moles. So what happened then was he was able to determine, or well, not determine, but theorize about something that he thought was called absolute zero, and it had to do with particle motion. So the absolute minimum temperature that occurs is at 0 Kelvin or negative 273.15 degrees Celsius. That's known as absolute zero. Absolute zero is, in theory, the lowest possible temperature that can ever be reached. It means as the particles are moving, they become slower and slower as temperature decreases, and eventually the particle motion will stop at 0 Kelvin. So he just developed a scale known as the Kelvin scale. Notice there is no degrees here, it's just called Kelvin. So we're degrees Celsius plus 273, or 273.15, is going to give us a Kelvin temperature. So absolute value is in theory. It's never been reached. It's come very, very close in a lab, tenths of a degree away, but never been reached yet. So volume is proportional to temperature with constant number of moles and constant pressure. So we're going to see it change proportionately as absolute temperature changes. So notice that we're always talking about must use Kelvin temperatures to get the right answer. So you'll convert from degrees Celsius to Kelvin, do the math, and convert back from Kelvin to degrees Celsius if necessary. It will not work. The math will not work with degrees Celsius. So at constant number of moles and constant pressure, the volume of an ideal gas changes proportionately with temperature, but it has to be absolute temperature. So here we have 1 atmosphere of pressure and the volume is a half a liter. We still have 1 atmosphere of pressure, but the volume doubled because we doubled the temperature, went from 200 Kelvin to 400 Kelvin. So notice this is constant and this is constant. What's changing is going to be the volume as we change the temperature. So for 2 trials, we said V1 over T1 is equal to K, which is also equal to V2 over T2. So the same constant is equal to V2 over T2. So we can get V1 over T1 is equal to V2 over T2. Now, I don't know about you, but my brain seriously refuses to remember fractions. It just doesn't like it. So whenever possible, I'm going to cross multiply and I'm going to remember the equations differently. So I'm going to actually remember this as V1 T2 is equal to V2 T1. Obviously, you are able to remember either of these. They are both the same equation. So they're both the same equation. They're just, I cross multiplied to get rid of the fractions because my brain doesn't like fractions. So these are the same equation. I will be using this one when I go through and do examples, just because that's how my brain works. Just remember that the T2 and the T1 are in the opposite place. If a balloon at 22 degrees Celsius has a volume of a half a liter, what will the volume be if the balloon is cooled to 4 degrees Celsius? V1 T1 is equal to V2 T2. So V1 T2 is equal to V2 T1. V1 is 0.500 liters. T1 is 22 plus 273, which is 295 Kelvin. V2 is what we're looking at. And if I have 4 plus 273, I get 277 Kelvin. For sig fig purposes, use the Kelvin temperature because that's where you do your math, and then you're going to end up coming back doing addition and subtraction. So usually you're going to have at least 3 sig figs. All right, so we need to find V2, so we're going to divide both sides by T1, and we get V1 T2 is over T1 is equal to V2. So V1, 0.5 liters. Now make sure you're careful, you want T2. T2 is 277 Kelvin divided by T1, which is 295. So one of the biggest mistakes people make is we invert the temperatures. 0.5 times 277 divided by 295. Ask yourself first what should happen. It's cooled, so the volume should go down, right? If you take that balloon outside and it's colder, the balloon gets smaller. 0.46949155254. And I'm going to say three significant figures, actually two significant, remember, we added that here, so it ends up being three significant figures, 0.469 liters. I want you to try this one, so pause it and try it, please. There are some things that you might need to think about. A lot of these are story problems. On a cool morning, 10 degrees Celsius, a group of hot air balloonists start filling their balloon using a large fan. After the balloon's envelope is 3/4 filled, they turn on the propane burner to heat the air. At what degree Celsius temperature will the air fill the envelope to its maximum capacity of 1,700 meters cubed? So V1, T1, V2, T2. And remember, we have V1, T2 is equal to V2, T1. V1 is 3/4 of full. Well, full is 1,700 meters cubed. So 0.75 times 1,700 should be what, 1,275? So maybe that was tricky. Yeah. Sorry, I put that in the wrong spot. I'm going to put it here. I just wrote that down in the wrong spot. All right, T1, 10 degrees Celsius. So 10 plus 273 is 283 Kelvin. V2 is 1,700 meters cubed, and T2 is our question mark. So we need to divide both sides by V1 to get T2. So V2 T1 divided by V1 is equal to T2. V2 is 1,700 meters cubed times T1 is 283 Kelvin divided by V1, which is 1,275 meters cubed. So the meters cubed are going to cancel. 1,700 times 283 divided by 1,275 is 373.333 repeating. This is Kelvin. It asks for degrees Celsius, so I need to subtract 273. 104.333 repeating. So our answer would be 104 degrees Celsius. So Gay-Lussac's law tells us that at constant volume, pressure is directly proportional to temperature. So remember, this is Kelvin temperature or absolute temperature. So that means P divided by T is equal to a constant, or P1 over T1 is equal to P2 over T2. So those are our equations because we can cross multiply and get this one, or we can remember it this way. So these are the relationships between pressure and temperature. Now you might have noticed this as the seasons change, or as it's refusing to change right now, that as the temperature changes, the pressure in your tires change. So in the spring and in the fall, it's extremely important to check the air pressure in your tires to make sure that it's where it's supposed to be, since temperature can have a drastic effect on pressure. So what do you think the graph will look like for this? This is known as directly proportional, so the graph would look like this. Remember, absolute temperatures or Kelvin temperatures are what we must use, otherwise it will not work. A cylinder of gas is filled to 150 atmospheres at 21 degrees Celsius. It's moved to a new location having a temperature of 27 degrees Celsius. What's the new pressure of the cylinder? Now we know we're going to use P1T2 is equal to P2T1 because it says Gay-Lussac's law at the top. But let's make our list. P1, T1, P2, T2. So P1 is 150 atmospheres. T1 is 21.0 plus 273, which is, so 21 plus 273, let's do our math in our head, is 294, right? 294 Kelvin. P2 is what we're looking for, and T2 is 27 plus 273, which is 300. So 27 plus 273 is equal to 300 Kelvin. We're solving for P2, so we need to divide both sides by T1. So P1, T2 divided by T1 is equal to P2. P1 is 150 atmospheres. T2 is 300 Kelvin divided by 294 Kelvin. So 150 times 300 divided by 294 is 153.0612245. Three significant figures would be 153 atmospheres. I want you to try the next one. So give this a try. A gas is confined to a rigid container and it exerts a pressure of 1,540 millimeters of mercury at a temperature of 300 Kelvin. What will be the new pressure of the gas if the gas is cooled to 250 Kelvin? So please pause it and try it. So I'm just actually going to click through it since you paused it and try it. So P1T2 is equal to P2T1. We want to divide both sides by T1 so that we can find P2. And we get this, P1 over T1, P1 T2 divided by T1 is equal to P2. So we do that and we get this equation. And we put this in. Now look, we have millimeters of mercury. I didn't actually give you what unit to answer in, so that's fine to answer in millimeters of mercury. But normally I will tell you what unit to answer in, so that way you don't have to worry about being in the wrong unit. So 1280 millimeters of mercury. The combined gas law is going to allow us to look at more than one variable. So it's going to express the relationship between pressure, volume, and temperature all in one equation. So we're going to take what we've learned and we'll put it all together. So P1, V1, Boyle's law, divided by T1. So if we were to cover up V1, we'd have P1 over T1, which is Gay-Lussac's law. If we were to cover up P1, we would have V1 over T1, which is Charles' law. But all of this is going to be equal to a constant, which also means P2 V2 divided by T2 is equal to that same constant. So we can say cross multiply P1 V1 T2 is equal to P2 V2 T1. So we're combining all of what we've learned into one equation now. So both of these equations are the same, and you can remember both of them, or you can remember either of them. Actually, in a little while, I'm going to show you just one equation that you have to know that you can relate all of these to. So combined gas law number one, let's try it together. If I initially have a gas at a pressure of 1.23 atmospheres, a volume of 23 liters, and a temperature of 205 Kelvin, I raise the pressure to 1.47 atmospheres, increase the temperature to 302 Kelvin. What is the new volume of the gas? P1 V1 T2 is equal to P2 V2 T1. I'm making my list. P2 V2 T2. So pressure 1, 1.23 atmospheres. Volume 1, 23 liters. Temperature 1 actually is given to you in Kelvin, not very common. P2 is 1.47 atmospheres. V2 is what we're looking for, and this is 302 Kelvin for T2. So we're looking for V2. We're going to divide both sides by P2 T1. Those cancel. So we get P2 T1. So P1 V1 T2 divided by P2 T1 is equal to V2. So P1 is 1.23 atmospheres. V1 is 23 liters. And T2 is 302 Kelvin. So make sure you don't invert your temperatures. You're using T2 here on the top. And on the bottom, we have P2, 1.47 atmospheres. Atmospheres are going to cancel. And T1, which is 205 Kelvin. Those cancel. So looking at that, I don't know why I have to do that, but it drives me crazy when it's way too long. All right, so 1.23 times 23 times 302 divided by 1.47 divided by 205 is 28.35102,041 liters. How many sig figs? We should have 2 because of the 23 liters, so this would be 28 liters is our new volume. All right, you try this one, so pause it and try it until you get stuck, and then I'll try to give you a hint, and then I want you to pause it and try it again after I give you the hint. A gas occupying 75.8 milliliters at standard conditions is heated to 17.4 degrees Celsius. While the pressure is reduced to 0.976 atmospheres, what is the new volume occupied by the gas? Combined gas law is P1 V1 T2 P2 V2 T1. Make our list. Pressure 1. Volume 1, 75.8 milliliters. Temperature 1. What? P2, 0.976 atmospheres. What's the new volume? And the new temperature is 17.4 plus 273. So 17.4 plus 273 is going to give us 290.4. Well, I don't know about you, but I feel like we're missing some things, huh? What does it look like we're missing? P1 and T1. I want you to reread the problem and remember what standard conditions are for a gas. STP for a gas is 273 Kelvin and 1 atmosphere, or you can use any other unit. But since we have atmospheres and we have Kelvin, definitely need to have Kelvin. But our pressure then is 1 atmosphere and 273 Kelvin. So go on and try this one now. Pause it and try it if you haven't already done so. And we're going to be solving for V2, so we divide both sides by P2 T1. So P1 V1 T2 divided by P2 T1 is equal to V2. P1 is 1 atmosphere times V1, which is 75.8 milliliters, and T2 is 290.4 Kelvin. On the bottom, we have P2, 0.976 atmospheres, times T1, which is 273 Kelvin. So 1 times 75.8 times 290.4 divided by 0.976 divided by 273 is 82.6139434343. Atmospheres cancel, Kelvin cancel, this is going to be milliliters. So the new volume to 3 significant figures would be 82.6 milliliters. And that's our combined gas law. Avogadro's law is going to relate the number of moles. So this is a little different than what we talked about with Avogadro before, but it is still related to his number and everything else. So it is related, but we won't be using the 6.02 times 10 to the 23rd. But Avogadro's law says that volumes of gas at the same temperature and pressure contain equal number of particles. So no matter what the gas is, this is one of those ones where we say no matter what the gas is, it doesn't matter. The identity of the gas, ID of gas, doesn't matter. If we have the same volume, we're going to have the same number of particles. So from the kinetic molecular theory, when we talked about some assumptions and other things, all gases have the same behavior, no matter what their identity. So they all have the same behavior. That means that gases that are having a larger volume will have a larger number of particles. So if it has the equal volumes of particles if it has equal volumes, they have the same number of particles. That just intuitively says if one has a larger volume, it must have a larger number of particles. But keep in mind, this is at the same, with all the other variables being kept constant. So this is known as molar volume. Well, we'll talk about molar volume in a minute. But this is Avogadro's law, and it says that the volume and the number of moles are proportional. So constant temperature and pressure, the volume and the number of moles are going to change proportionately. Look at this volume, 22.4 for 1 atmosphere and 1 mole. So the pressure is going to be remaining constant, so we don't look at that one. But if we increase the number of moles, we double it, we also double the volume. No matter what the gas is, if I double the moles, I'm doubling the volume. If I cut the moles in half, I'm going to half the volume. So V over N is equal to a constant K, or V1 over N1 is equal to K, and V2 over N2 is also equal to K. And you could use initial and final too, but we usually just use V1 over N1 is equal to V2 over N2, or V1 N2 is equal to V2 N1. Now we've talked about what these relationships mean in the past, and we've said that these are moles, right? But we didn't first call them moles, we first called them molecules. Do you remember way back when? So the first thing we did was we said 3 molecules of hydrogen react with 1 molecule of nitrogen to produce 2 molecules of ammonia. And then we talked about Avogadro's relationship, and we said, well, actually, we can call these moles. We said 3 moles of hydrogen react with 1 mole of nitrogen to produce 2 moles of ammonia, because we related them all through Avogadro's number, and we're changing them all the same. Well, guess what? I'm here to tell you that these can actually be considered volumes as well. Since volume and the number of moles are related, we could say 3 volumes of hydrogen react with 1 volume of nitrogen to produce 2 volumes of ammonia. Now, volumes is just a unit. So volumes means any volume unit, as long as they're all the same. So milliliters, liters, anything like that we use, these could all be milliliters. They could all be liters, as long as they're all the same, any volume unit. So what this is going to allow us to do is to convert between volumes of a gas. And I'm going to show you a long way and a short way to do this, just so that you can see that these coefficients are volume coefficients as well when we're talking about gases. So molar volume is, so we're talking about here how volume and the number of moles are related, right? So V1 over N1 is equal to K, right? So if they're related like this, at standard temperature and pressure, 1 mole is equal to 22.4 liters. This is known as molar volume. It's only for gases. Can't use it with liquids. So 1 mole of any gas, I'll watch it, it's gonna, for any gas, because all gases are gonna have the same behavior. So 1 mole is equal to 22.4 liters. This is going to allow us to convert from moles to liters. So let's give it a try. Why is that important? Because I can't measure in moles in the lab. You're planning an experiment that requires 0.0580 moles of NO gas at STP. What volume of gas will you need? 0.0580 0.0 moles of NO. For every 1 mole of NO, how many liters? 22.4 liters. Okay, I can write of NO. So I'm going to take the 22.4 and I'm going to multiply by 0.0580 and I get 1.2992 liters of NO. Three significant figures, I get 1.30 liters of NO. That's what I need to measure out. That's what I need to use in the lab. I can't measure moles. I have to have this a measurable quantity so I can go between moles and volume for gases by using molar volume. All right, xenon reacts with fluorine gas. I want you to try this. Take it one step at a time. Don't be afraid of it. Xenon reacts with fluorine gas to produce the compound xenon hexafluoride. Write the balanced equation. So this is number one. This is number one for this reaction. If a researcher needs 3.14 liters of xenon hexafluoride for an experiment, what volumes of xenon and fluorine should be reacted? Assume all volumes are measured under the same conditions of temperature and pressure. So xenon reacts with fluorine. What is special about fluorine that we need to remember? So fluorine, this is a gas, this is a gas, to produce xenon hexafluoride. So I need 3 of those. And this is a gas. All right, so that one's done. The researcher needs 3.14 liters of this gas. How much of the xenon and the fluorine should be reacted? So it's 3.14 liters of XeF6. For every 22.4 liters of XeF6, we get 1 mole of XeF6. So this is how we're used to doing things. We go to moles, so now we're in moles, and for every 1 mole of XeF6 that forms, I need 1 mole of xenon. So 1 mole of xenon is 22.4 liters of xenon. So this is our new conversion factor. And when we do this, you should get 3.14 liters of Xe are required. But I would like you to take a look at this. I divide by 22.4 and I multiply by 22.4. And the only thing I did in the middle that was different was I multiplied by the mole ratio. But if you look back a couple slides, we went over how that mole ratio could also be considered for gases a volume ratio. So we could put this as a volume ratio, which I'll show you how to do with the next one. So the next one says 3.14 liters of XeF6 are required. For every 1 liter of XeF6 that's required, I need 3 liters of F2. And again, it doesn't have to be in liters, it can be in any volume unit. So 3.14 times 3 is 9.42 liters of F2. So 9.42 liters of F2, 3.14 liters of xenon are required. So the ideal gas law is actually going to combine all the gas laws that we've learned. It describes the physical behavior of an ideal gas. Remember, an ideal gas is actually going to be something that does not really exist. It's in fact just a really good estimation of gas physical behavior at or around standard temperature and pressure. So we can look at the pressure, volume, temperature, and the number of moles of a gas all in one equation. And that equation is PV equals nRT. Pressure, volume, number of moles, the gas constant, and temperature in Kelvin. So we can have all of those and we can determine the physical behavior of an ideal gas. The gas constant, where does R come from? So R, the one that we're going to use most frequently, is 0.0821, and the units are liters times atmospheres over mole times Kelvin. Those are big units, but where does it come from? So 1 mole of gas at 273 Kelvin, 1 atmosphere, occupies a volume of 22.4 liters. These are all STP values. So if you were to solve for R in the PV equals nRT equation, you would have PV divided by NT, and you would get pressure is 1 atmosphere, volume is 22.4 liters, N is 1 mole, and T is 273 Kelvin. And if you were to do that with those units, you would get 1 times 22.4 divided by 1 divided by 273, you get 0.082051281. And that's liters times atmospheres over mole times Kelvin. So that's where R comes from. So if you forget it, you can calculate it. But there are a lot of different units. So liters times kilopascals use 8.314. These are the ones that are often used in physics because you're using different units in physics. So this is just a table of all the different values of R. This is the one that we're going to be using most of the time in chemistry. How many moles of gas at 120 degrees Celsius does it take to fill a 1 liter flask to a pressure of 1.33 atmospheres? PV equals nRT. Give it a try. Pause it, give it a try. P equals V equals N R N T. Pressure, 1.33 atmospheres. Volume, 1 liter. Temperature, 120, okay, plus 273 is 393 Kelvin. N, how many moles is what we're looking for, and R, 0.0821 liters times atmospheres over mole times Kelvin. So we're going to solve this for N, so we divide both sides by RT, and we get PV divided by RT equals N. Pressure is 1.33 atmospheres. Volume is 1.00 liters. R is 0.0821 liters times atmospheres over mole times Kelvin. And T is 393 Kelvin. Look at the units. Atmospheres cancel, liters cancel, Kelvin cancels. Moles are in the denominator, so they're actually in the numerator, which is good because we're looking for moles. 1.33 times 1 divided by 0.0821 divided by 393 gives us 0.0412207542. 3 significant figures, 0.0412 moles of gas. And that's all there is to it. You can see me click through it if you'd like. All right, you give it a try. What volume would be occupied by 100 grams of oxygen gas at a pressure of 1.50 atmospheres and a temperature of 25 degrees Celsius? So you're going to need to do an extra step in this one, I'll tell you that much. So give it a try and see what you can do. So PV equals nRT. P, V, N, R, T. What volume would be occupied by 100 grams? This is O2. 32 grams O2 for 1 mole. Is 3.125 moles O2. 1.50 atmospheres for the pressure, and a temperature of 25 plus 273 is 298 Kelvin. And R, 0.0821 liters times atmospheres over mole times Kelvin. You should always check to make sure the units are proper. So we have atmospheres and atmospheres, Kelvin and Kelvin, moles and moles. So if you didn't convert this, from grams to moles, you would notice when you check the units here and see that they don't cancel. That's when you'll know that you have a problem. So it's good to check your units. It's usually easier at this point to change the units of the individual variable than it is to change the units of R, but that is up to you. We're solving for V, so we're going to divide both sides by P. So we get volume is equal to nRT divided by P. So we have N, 3.125 moles of oxygen times 0.0821 liters times atmospheres over mole times Kelvin, and T is 298K. We divide all of that by 1.50 atmospheres. Let's do a unit check. Moles cancel with moles, Kelvin with Kelvin, atmospheres with atmospheres. We're going to be left in liters, which is a volume unit, so that's a good sign. 3.125 times 0.0821 times 298 divided by 1.5 is 50.97041667. Again, we still have three significant figures, so 51.0 liters of O2. So if R is in your problem, you need to make sure the units are the same as those in R. So we would need to make sure our pressure unit is atmospheres, our volume is liters, and then our temperature is Kelvin and N is in moles, right? Because in the last problem it was in grams. So if R cancels out, you can have units be anything really except for temperature, which must always be in Kelvin. So volume could be milliliters or liters as long as they're the same. They have to be the same. So we can't compare apples and oranges, they must be the same. So whatever that is, if R cancels out, if we're using any of the Boyle's, Charles, Gay-Lussac laws or Avogadro's law, that doesn't matter as much, but temperature must be Kelvin because that's the only way it relates. So gases we can also look at density, and we do use the density of gases quite frequently. So the lifting power of gases, we use most commonly for balloons and such, we use helium. So in order for a balloon to rise, it has to be filled with gas considerably lighter than or less dense than the air in order for it to rise, because it's got to compensate for the balloon that's holding the gas and anything that's added to it, because remember the gases have mass. So did you ever see the movie Up, like one of the cutest movies ever? In order to lift up that house, they needed a lot of balloons, but they also needed large balloons that have a lot of gas in them. And helium may or may not have lasted that long, but it was a cute movie nonetheless. So the density of a gas is dependent on its pressure, temperature, and its molar mass. So we use helium because helium has a molar mass of 4. But there is a gas that has half the mass of helium, and that's hydrogen. So in order to use an even lighter gas, we could use hydrogen, but that becomes dangerous. Okay, so in order to achieve a low density, we want to start with a low molar mass or by heating the gas. Well, hydrogen is flammable. So we don't want to use hydrogen because if you look up the Hindenburg, you will see why we don't want to use hydrogen. While it is an excellent lifting gas, being flammable causes way too many problems and we can't use it for anything that is of importance. So if it has a low molar mass, the lowest molar mass that we can use with an inert gas is helium, or we can heat the gas like a hot air balloon. If you've never been on a hot air balloon, it really is hot. The burner is really hot next to your head. So we can actually convert the ideal gas equation so you don't have to remember another equation to include density. or at the end, you can just remember this equation. That's fine too. So we start with PV equals nRT. In order to have density in there, density is equal to mass divided by volume, we need to have mass in there. Well, we can put in for N, how do we find moles? To find moles, we take the mass divided by the molar mass, which is what we wrote in the next part, M divided by molar mass. So mass divided by molar mass goes in here in place of M, because that's how we find moles. So now we have mass and we have volume, we just need to move it around so that we have them on the same side of the equation. So we are going to move this around so that volume comes over to this side of the equation. So mRT, the mass, times RT, divided by the volume times the molar mass. And then we can pull this out. This is all just moving things around mathematically. It's all okay. This is equal to density. So we can then say dRT, density, times R times temperature divided by molar mass is equal to pressure. So if we wanted to solve that then for density, we would say density is equal to pressure times molar mass divided by RT. And I think I actually don't have it in there. So this would be how to solve for density. So you can always just remember this, or you can find it from the ideal gas law. And that way the ideal gas law is technically the only one you need to memorize. So there's two principal lifting gases, hydrogen and helium, but hydrogen is too dangerous because it's flammable. Helium has less lifting power, half, because it has twice the mass. And it's also very rare, believe it or not. A helium escapes the atmosphere, and when I was running the Pure Gas Lab at Airgas, we were always at a helium shortage. It also has no tendency to burn, which is good, but it's more expensive. So hot air balloons use hot air, and they do that because raising the temperature allows that to have more lifting power because it lowers the density of the gas. So I want you to try this one on your own and see what you find. So what is the density of oxygen in grams per liter at 25 degrees Celsius and 0.850 atmospheres? So the density is mass divided by volume. Remember that. Pause it and try it. So we just said that density is equal to pressure. Want to go back and check? So pressure times molar mass divided by RT. And we can always, excuse me, we can always solve for that as well. So we have pressure, 0.850 atmospheres, and the molar mass of oxygen is 32 grams per mole. R, 0.0821 liters times atmospheres over mole times Kelvin. And T, in this case, is 25 degrees Celsius. So 25 plus 273 is 298 Kelvin. So here, Kelvin cancels, atmospheres cancel. We have grams over moles and liters over moles. So moles are in the denominator here, and these are actually in the numerator, so they do cancel because it's in the denominator and the denominator. So our units are going to be grams per liter, which is good because that's what it asked for. That's a good sign. 0.850 times 32 divided by 0.0821 times divided by 298 gives us 1.111756002 grams per liter. Three significant figures, 0.11, 1.11 grams per liter of oxygen. And that's it, right? Pretty simple. I want you to try this one. Again, don't let the amount of words scare you. There's actually two different ways to do this problem. Just look at what you're looking for. So we're looking for the molar mass. Molar mass is grams divided by moles. So you have grams, You can find moles and then divide them, or you can use the D is equal to PMM over RT and solve for molar mass. So that would be DRT divided by P is equal to molar mass. So in that case, you would have to get density. So either way, you're going to have to do a little bit of something. But let's read it. I want you to try it. A volatile liquid was placed into a 200 milliliter flask and vaporized. So the volume is 200 milliliters. You cool the flask so that the vapor condenses and you weigh the flask and the liquid. After you subtract the mass of the flask, you find that the remaining mass is 0.970 grams. So dividing these will give us density. The temperature of the boiling liquid was 99 degrees Celsius. So 99 plus 273 is 372 Kelvin. And the pressure was 733 millimeters of mercury. Well, I can't use that, so I need to just divide by 760 and get 1 atmosphere. So 733 divided by 760, and I get 0.9644736842. So I can divide these and say density is mass divided by volume. So 0.970 grams divided by, now 200 milliliters. If I want to put this in there, I'm going to need this in grams per liter. So I need to convert that to liters by dividing by 1,000, and I get 0.2 liters. 0.970 divided by 0.2 is 4.85 grams per liter. So now I have density, I have R, I have T, and I have P. So let's stick that in there and say molar mass is equal to 4.85 grams per liter times 0.0821 liters times atmospheres over mole times Kelvin times the temperature of 372 Kelvin divided by the pressure, which is 0.9645 atmospheres. Let's take a look at the units. Liters cancel, Kelvin cancels, atmospheres cancel, and we're left in grams per mole, which is a nice molar mass unit. So 4.85 times 0.0821 times 372 divided by 0.9645 gives us 153.576. That's all I'm going to keep because I'm running out of room. And we only need 3 anyway, so 154 grams per mole. Big scary problem, but you definitely can do it. You just got to remember what each of the pieces mean and put them together.